5.6 Trends in Periodic Properties. The electron configurations of atoms are an important factor in the physical and chemical properties of the elements and in the properties of the compounds that they form. In this section, we'll look at the valence electrons in atoms, the trends in atomic size, ionization energy, and metallic character. Going across a period, there's a pattern of regular change in these properties from one group to the next. Known as periodic properties, each property increases or decreases across a period, and then the trend is repeated in each successive period. We can use seasonal changes in temperatures as an analogy for periodic properties. In the winter, temperatures are cold and become warmer by spring, and by the summer, outdoor temperatures are hot but begin to cool by the fall. By winter, we expect cold temperatures again as a pattern of decreasing and increasing temperatures repeats for another year. Group number and valence electrons. The chemical properties of representative elements are mostly due to valence electrons, which are electrons in the outermost energy level. These valence electrons occupy the s and p sublevels with the highest principal quantum number n. The group number indicates the number of valence electrons for the elements in each vertical column. For example, the elements in group 1a, such as lithium, sodium, potassium, still have one electron in an s orbital. Looking at the sublevel block, we can represent the valence electron in the alkaline metal group 1a as in S1. All the elements in group 2a, the alkaline earth metals, have two valence electrons, 2s2. The halogens in group 17, have valence electrons, 2s2, 2p5. We can see a representation of the outermost s and p electrons for the representative elements for periods 1 to 4 in Table 5.3. Helium is not included in group 8a because it is a noble gas, but it only has 2 electrons in its complete energy level. So 1s1, 1s2, 2s1, 2s2, 2s1, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, 2s2, 2p6. Electron dot symbols. An electron dot symbol is a convenient way to represent the valence electrons, which are shown as dots placed on the side, top, and bottom of the symbol of the element. 1 to 4 valence electrons are arranged as single dots. When there are 5 to 8 electrons, one or more electrons are paired. Any of the following would be acceptable electron dot for magnesium, which has 2 valence electrons. Electron symbol dots are selected elements are given in Table 5.4. Atomic size. The atomic size of an atom is determined by the distance from the valence electrons from the nucleus. For each group of representative elements, the atomic size increases, going from the top to the bottom because the outermost electrons in its energy level are farther from the nucleus. For example, in group 1A, lithium has valence electron in energy level 2, sodium has valence electron in energy level 3, potassium has valence electron in energy level 4. This means that potassium atom is larger than sodium atom, and sodium atom is larger than a lithium atom. The atomic atom size increases down a group, but decreases going from left to right across a period. The atomic size of representative elements is affected by the attractive forces of the protons in the nucleus of the electrons of the outermost level. For the elements going across a period, the increase in the number of protons in the nucleus increases the positive charge of the nucleus. As a result, the electrons are pulled closer to the nucleus, which means that the atomic size of representative elements decreases, going from left to right across a period. The size of atoms of transition elements within the same period changes only slightly because electrons filling the d orbitals rather than the outermost energy level. Because the increase in nuclear charge is cancelled by an increase in d electrons, the attraction of the valence electrons by the nucleus remains about the same. Because there's little change in the nuclear attraction of valence electron, the atomic size remains relatively constant for the transition elements. Ionization energy. In an atom, negatively charged electrons are attracted to the positive charge of the protons in the nucleus. Therefore, energy is required to remove an electron from an atom. The ionization energy is the energy needed to remove one electron from an atom in the gaseous state. When an electron is removed from a neutral atom, a cation with a positive 1 charge is formed. The attraction of the nucleus for the outermost electrons decreases as the electrons are farther from the nucleus. Thus, the ionization energy decreases going down a group. However, going across a period from left to right, the positive charge of a nucleus increases because there is an increase in the number of protons. Thus, the ionization energy increases going along the left to right to the periodic table. In summary, the ionization energy is low for metals and high for nonmetals. The high ionization energies of the noble gases indicate that their electron configurations are especially stable. Metallic character. In section 4.2, we identified elements as metals, nonmetals, and metalloids. An element has a metallic character is an element that loses valence electrons easy. Metallic character is more prevalent in elements, metals, on the left sides of the periodic table and decreases going from left to right across a period. The elements nonmetals on the right side of the periodic table do not easily lose electrons, which means they are less metallic. Most of the metalloids between the metals and the nonmetals tend to lose electrons, but not as easily as metals. Thus, in period 3, sodium, which loses electrons most easily, would be most metallic. Going across from left to right in period 3, metallic character decreases to argon, which has the least metallic character. For elements in the same group of representative elements, metallic character increases going from top to bottom. Atoms at the bottom of any group would have more electron levels, which makes it easier to lose electrons. Thus, the elements at the bottom of the group of the periodic table would have a lower ionization energy and more metallic compared to the elements at the top. A summary of the trends and periodic properties we have discussed is given in Table 5.5. Valence electrons remains the same, going from top to bottom, and increases as it goes across a period. Atomic size increases due to the increase in the number of energy levels as it goes down a group, but it decreases with the number of protons increases, which strengthens the attraction of nuclei for the valence electrons and pulls them closer to the nucleus. The ionization energy decreases as it goes down a group because the valence electrons are easier to remove when they're farther from the nucleus. They increase as they go across a period because the number of protons strengthens the attraction of the nucleus and the more energy is needed to remove an electron. The metallic quality increases because the valence electron as it goes down a group are easier to remove when they are further from the nucleus. And they decrease as the number of protons increases across a row, which strengthens the attraction of the nucleus for the valence electrons and makes it more difficult to remove a valence electron.